All right. Well, this first lecture will consist of a review of the multivariate normal distribution. The first thing I want to remind you is why we study the normal distribution in general. One of the central reasons that we study the normal distribution is because it arises naturally in many different parts of the sciences and in general, as you'll see in environmental sciences, in physics, and in engineering. So here are some examples. So it arises naturally in diffusion, in modeling diffusion and Brownian motion. It is well known that, for instance, the distance traveled by particles suspended in a fluid, you can think of smoke particles or pollen particles floating in air, follows a normal distribution over time. This is a theoretical model of their motion, but real-world observations confirm that the multivariate normal distribution is an appropriate model for these types of processes. Another place where we see the multivariate normal distribution is in the distribution of measurement errors across fields. For instance, if you think of measurements in physics or chemistry, measuring the same constant multiple times results in some small random errors every time you measure. Typically, it has to do with some random variation in the instruments and their precision. The measurements will be normally distributed approximately, and if the instrument is correctly calibrated, they will be normally distributed around the true value. Another example of variables that are well modeled by a multivariate normal distribution are various animal characteristics in ecology, for instance, or mathematical biology. Some different traits, like morphological traits, think of, for example, the wingspan of birds in a specific species, or, for instance, the length of leaves on a single tree, show normal variation. If you think of, for instance, a species of beetle, and you look at measuring the length of each individual and the width of each individual's body, you typically find that larger individuals have both larger length and larger width, and smaller individuals have both smaller length and smaller width. So there's dependence in the different features of these animals. And that can be well modeled by a normal distribution, as we'll see in a second. More generally, I'm going to mention here the central limit theorem. This is a key result in statistics that essentially implies that the normal or Gaussian distribution can be used to model any high-dimensional system where the outcome is the result of many small additive factors. Examples include genetics, measurement errors, or even market fluctuations, if you think of an economic system. So these are all places where the normal distribution naturally arises. So while we're going to be studying the theoretical model, the multivariate normal distribution and its theoretical representation, in fact, there are many cases when working with real data where we see these normal distribution arising naturally. Let me give you an example. This example comes from the 1930s. It is a real data set of measurements on iris flowers. This data set was originally compiled by Ronald Fisher in 1936. It is a well-known example of data that is well modeled by a multivariate normal distribution. And as I mentioned to you before, in nature, traits rarely vary in isolation. So the multivariate normal model allows us to capture these dependencies. So the data set itself consists of 150 observations of 3 species of iris flower. And for each flower, we record the following characteristics. So let's define a vector xi. That would be for the ith individual, the ith flower. And for each individual, we're going to record what I'm going to call xisl, which is the sepal length. So that's the length of one part of the iris flower. The second variable will be the sepal width, SW. Then we're going to look at the petal length, PL subscript. And the petal width, PW. So those 4 variables are recorded on each individual. And we will see that the normal distribution is a nice way of describing what we actually see in nature for this particular data set. Now, the 3 different species of iris flowers that are covered in this data set, Setosa, versicolor, and virginica, all have slightly different distributions. They're all well modeled by multivariate normals, but we're only going to consider one of them. We're not going to look at the mixture of these 3 distributions. So I will just look at the Setosa data set, and let's pull up our R code. And this is the R code that has the following name on the GitHub page. Okay. It is iris underscore data underscore visualization .r. So this is the R code that I'll be using to showcase this particular data set. This is available on the GitHub page. I'm going to run this code, and if you have any questions about the code, feel free to ask me after the class or ask Eric during the practical TA sessions. So this is the plot that the code produces. Let me summarize what you see here. On the diagonals, you see histograms for each individual characteristic of the Setosa iris marginally, so separately. So the sepal length, you can see a histogram for the distribution of sepal length, a histogram for the distribution of sepal widths, of petal lengths, and petal widths. One thing to notice here, that while not, you see a little bit of noise in each variable, you can see some features in common. First of all, the distribution of these individual variables appears to be unimodal. So there's just one single mode in the middle, and most of the probability mass, most of the data occurs within 2 standard deviations of the mean. You also see some degree of symmetry, although we do have a pretty small number of observations. So symmetry is not necessarily something that we would expect to see perfectly in this case, but there is a little bit of it, except for petal width. This petal width, of course, seems to be highly asymmetric. Now, if you look at the off-diagonal parts of this plot, you can see the actual scatter plots of the variables. So this one, for instance, shows you the scatter plot of sepal length versus sepal width. And as you can see, they are positively correlated. A larger sepal length is associated with a larger sepal width, just like I mentioned with the beetles before. So there is some dependency between these variables for each individual. And here again, we have the relationship between sepal length and petal length. As you can see, that relationship is less strong. That dependence is less strong. But if you look at the dependence, for instance, between petal length and petal width, again, we have sort of a positive correlation between them. Okay, as one increases, the other one is more likely to increase, and vice versa. These are common features of the distribution we'll be studying in this lecture, the multivariate normal distribution. So hopefully this data set has shown you that we need a statistical model that captures the types of characteristics that we see here. And these are actually quite common, as I mentioned to you, in ecology, engineering, all over the sciences, and physics and chemistry. So let's go back to our notes. And discuss how we would model this kind of data. So in order to model this data, I'm going to introduce the multivariate normal distribution, or the Gaussian distribution. All right, let's begin with a definition. A random vector x defined as a column vector with elements x1 to xk follows a multivariate normal distribution if its joint probability density function is as follows. So we have a constant coefficient in the front, which depends on the determinant of this covariance matrix, sigma, times an exponential of the so-called Mahalanobis distance between the data, the random vector, and its mean. Here, the mean vector mu is defined as the expectation of the random vector x The covariance matrix which I'm going to call sigma, is the expectation of x minus mu times x minus mu transpose. And the covariance must be symmetric and positive definite. We will see later also we will look at some additional interpretations of this covariance matrix. Another note that I'd like to make is that the probability density function uniquely defines the distribution of a random variable. So any random vector like x with this probability density function is necessarily a multivariate normal random vector with mean mu and variance sigma. So this is the definition of a multivariate normal random vector. Next, I'd like to talk to you about the geometry of this distribution. And this is where we're going to see some of those characteristics come up that we saw when we looked at the iris data. So we're going to look at features of the multivariate normal distribution. So let's talk about the geometry of this distribution. So the geometry of multivariate normal random variables density is defined by, as I mentioned, this Mahalanobis distance. This is where the dependence of the PDF on x comes from. It's a function of this exponent here. And this will be the square root of x minus mu transpose times the inverse of the covariance matrix sigma times x minus mu. This defines surfaces of constant density or level sets, which are hyperellipsoids. We're going to visualize these in just a moment. And for this, I'm going to show you some additional R code, and I will refer to it here in the slides so you can pull it up later. So the R code that allows you to plot these level sets is bivariate normal level sets.R. And the figure that you will obtain looks like this. I'm going to show you how to produce a bivariate normal contour. And this is the contour of the theoretical distribution of the multivariate normal random variable. And of course, in practice, you will see the data that is sampled from this distribution does not necessarily have these exact features, especially for small samples. But as the sample size grows, you begin to see more and more features of this theoretical distribution. And we'll see that in just a moment. So these are contours or level sets of a bivariate normal distribution. And in 2D, they're going to be ellipses. This is mu, this vector mu right here. And we will see that the axis of principal variation are related to the eigenvectors of this covariance matrix. So if you run this R code, I probably won't do it during the class, but you'll see how to produce this exact plot. So as I mentioned, if you do an eigen decomposition, as follows. So you let this covariance matrix sigma equal to V lambda V transpose, where the columns of V are going to be orthogonal and lambda is going to be a diagonal matrix of eigenvalues. We will see that the eigenvectors in V define the principal axis, the principal directions of greatest variation in the multivariate normal distribution. Now the eigenvalues lambda I, and these are going to be the diagonal entries of that matrix lambda, define the variance or the stretch along those axes. So going back to our image from before, the eigenvector associated with the largest eigenvalue is shown here. And the eigenvector associated with the second largest eigenvalue is shown here. So you can see the directions of the principal directions of the variation. So now we see how these parameters can be interpreted in terms of the geometry of the multivariate normal distribution. Okay. Next, let's talk about some properties of multivariate normal random vectors or random variables. So these are going to be crucial for the finding and doing inference on Gaussian processes. Well, so an important property of multivariate normal random variables are their stability under linear transformations. So this is why we often use them for linear models in statistics. So if you've taken advanced statistics courses, you have typically worked with multivariate normal distributions in the context of linear modeling. So I'm going to introduce the following theorem. We will be proving this theorem as part of homework 1. If X follows a k-variate multivariate normal distribution with mean mu and variance sigma, then for any constant matrix, A, I'm going to call it m by k here, and vector B, and that's just going to be an m by 1 column vector, we have the following. If you define a new random vector y as ax plus b, what this implies is that y is now also normally distributed and has the mean a mu, which is a transformation of the original mean by the transformation defined by this matrix A, shifted by this vector B, so plus B, and variance covariance matrix A sigma A transpose. Yes, there's a question.
Yes, so what do we mean by a normal distribution with zero variation? Or do we not mean anything, and how does that
Yes, of
work?
course. Right. So if the sigma, so you're asking if the sigma matrix is 0, right?
No, not sigma because it's positive, but constant matrix A or something that would make the variance zero.
Oh, I see, I see. Oh, that's right, that's right. Yeah, so that would define, right. So that would define
Because
so
technically it wouldn't be positive or
right,
positive
exactly.
definite matrix because sigma should be positive by
Yes,
your
exactly.
definition.
Yes, that's correct. Yeah. So in this case, yes. So this leads to a degenerate distribution. So we call y having a degenerate distribution. So we will sometimes say the density is a direct delta probability density function. So we have a special name for it. It's no longer technically a normal distribution. So you're right. Is that your question? Yeah, so why
Thank you.
have the degenerate distribution at a mu plus beta in that case? Very good. Yeah, that's an excellent point. All right, so the key consequences of this theorem are the marginalization property. So if X is multivariate normal, then any subset of its components is also jointly multivariate normal. Okay, so you can use this to show that fact. I'll write it down in just a moment. And there's also standardization. We can standardize random variables x using a transformation that allows us to write the transformed variable as standard normally distributed. The property is fundamental for generating multivariate normal samples from standard normal noise. So if we have pseudo-random number generator, and we're able to generate standard normal, so that is normal with mean 0 and identity covariance random variables, then we can use this theorem to obtain random variables that are also to obtain random variables with a specific mean and covariance. It also allows us to do whitening of the data by removing the mean and decorrelating the variance. So let's have a look at some additional R code next. Okay, and the R code is, let's see here, what is it? It's bivariate normal sampling. Let's have a look. So what I'm going to do here is I'm going to generate 500 realizations from a bivariate normal distribution with mean vector with elements 2 and 5 and covariance matrix that has both diagonal and off-diagonal entries. So in other words, we have some correlation in this particular data set. Let's look. And all right, so hopefully you're seeing my screen. So here are 500 realizations from the bivariate normal distribution. The mean of the simulation is defined to be the vector 2 and 5. So you can see that's exactly where this yellow rectangle lies. And if you do an eigen decomposition of the covariance matrix, you'll find these two directions of maximum variation. Okay. The red one here is associated with the largest eigenvalue, and the green one is associated with the smaller of the two eigenvalues, as you can see. So just like the theoretical version, we can see this same pattern occurring when we sample from that distribution. I'm also using the theorem that we just discussed to sample these bivariate normal realizations, starting from a standard normal random variable that is generated using pseudorandom number generation. So I encourage you to have a look at the code in detail, although unfortunately I won't have time during this lecture to go through the code. All right, so the key consequences of this theorem, as I mentioned before, the first one is marginalization. So if X is multivariate normal, any subset of its components is also jointly multivariate normal. And standardization. So if we decompose the covariance matrix sigma into sigma to the 1/2 times the transpose of sigma to the 1/2. So for instance, you may use Cholesky decomposition to do this. Suppose that Z is a standard normal random variable. So standard normal means it has a mean of 0 and that the covariance matrix is the identity matrix. And suppose that X is given by mu plus sigma to the 1/2 times Z. Then X will follow a normal distribution with mean mu and covariance matrix sigma. Okay, so that's one way that we can sample random variates from this distribution if we only have access to sampling from a standard normal. And then also conversely, if we start out with a random variable X, which is multivariate normal mu sigma, then we can, we call this standardization. We can standardize X using the following transformation to obtain a standard normal random variable. In other words, we can remove the mean and decorrelate the variance, the covariance matrix. So those are some useful properties of the multivariate normal distribution. Some additional properties that may be of interest are partitioning and conditioning. We will see these a lot when we work with Gaussian processes. So this is related to what happens when we partition a multivariate normal random vector into subvectors and look at their conditional distribution. We will also define, first I'll tell you what the result is, and I'll explain what the notation means. Then the conditional distribution x1, given that x2 is equal to some specific value, lowercase x2, will be multivariate normal with the following means: mu 1, 2, 1, the conditioning symbol, and 2, I'm going to define these in a second, and sigma 1, conditioning symbol 2, okay? Where the conditional mean is defined as follows: x1, mu mu 1, conditioning symbol 2, is mu 1. Okay, so that's going to be the mean partition corresponding to x1. plus sigma 1, 2. Now this is going to be the sigma submatrix corresponding to the covariance between the first and the second x. Oh, sorry, the first and the second x. There we go. That's going to be the conditional mean. So as you can see, the conditional mean of x1, given that x2 follows this, has this value, lowercase x2, is going to be equal to the mean of x1, okay, plus this transformation of x2 minus mu. Okay, so we're going to take x2, we're going to look at how x2 and x1 covary, okay, and then we are going to map that into into the mean of x1. All right. The conditional covariance is given by sigma 1 conditioning symbol 2. It's going to be the 1, 1 submatrix of sigma minus the 1, 2 submatrix times the 2, 2 submatrix inverse times the 2, 1 submatrix. And this is also known as the so-called Schur complement. So if you can define a joint multivariate normal distribution between two random vectors x1 and x2, you have a closed form distribution for their conditional distribution. Yes.
Yeah, I was just wondering whether the fact that this matrix sigma 1, 1, 2 is positively definite obvious, or why is it positively definite?
That's a good question. Let me leave that until the end of the class. But essentially, we need the matrix also to be full rank. So we'll talk about that in the homework as well. But let's save that question until the end of the class. That's a really nice question. I'm going to continue on with the rest of the material first, if you don't mind. Would that be all right?
Yeah, sure, thanks.
Okay, perfect. Thank you. All right. Yeah, those are some great questions. And we will talk about also yes, obviously sigma has to be invertible. So, all right. So let's talk about moment generating functions. All right. So the reason why we're going to introduce this notion of a moment generating function is because we want to prove some results such as the one that you just saw on partitioning and conditioning. We're going to try to prove this theorem that I introduced earlier about linear transformations of multivariate normal random vectors. One of the tools that we use for that is the moment generating function. Like the probability density function or the cumulative distribution function, the moment generating function uniquely determines a distribution. But sometimes it's easier to work with than the probability density function for proving certain results. In fact, for homework 1, question 2, you'll be using this moment generating function to prove the theorem on linear transformations. So here's the definition. First, let X be a multivariate normal random variable with mean mu and variance sigma. let this be a k-dimensional multivariate normal random variable. The moment generating function, or MGF, is defined for any vector t in Rk as follows. This you might have also seen referred to as the Laplace transform. And for the multivariate normal distribution, it has the following form. It's the exponential of t transpose times mu plus 1/2 t transpose sigma t. The MGF, the moment generating function, uniquely defines a distribution. So to prove the theorem on linear transformations, you will need to define the moment generating function of x, and then find what the moment generating function of y would be, and then relate it back to this form of a moment generating function, and realize that y is also multivariate normal, and read off the mean and the covariance matrix. Okay, so that is called the moment generating function. And for now, this concludes the section on review of multivariate normal distribution, but I do want to mention a few things, and I know we're running over time, so I apologize for that. So I will answer the remaining questions at the end of the class. But first, I want to tell you a little bit about inference, and this will be critical when we talk about Gaussian processes. Suppose that we have some data and we have modeled it as a realization of multivariate normal random variables. Okay, that is what we would call our data generating model, or our likelihood model. Okay, so suppose that we observe some data as realizations of n independent multivariate normal random variables. Let's call this data y1 to yn. And we assume that they are independent and each is multivariate normal with mean mu and variance sigma, or covariance matrix sigma. Here, mu and sigma are so-called population quantities. Once we know mu and sigma for sure, then we have fully defined the data generating model. However, in practice, population quantities are rarely known. So these population parameters, mu and sigma, are going to be what we will try to estimate. All right, next I'm going to define what's called the likelihood function. So I will refer to the likelihood function as the joint density of the data, okay? In the classical view to a statistical inference, the likelihood function is indeed the joint density of the data, but viewed instead of a function of the data as a function of the parameters. Broadly speaking, there are two philosophies for statistical inference. The first philosophy, the first perspective, is called classical inference or frequentist inference perspective. And here, a statistical inference takes the form of two steps. The first step is to find an estimator that is a statistic or a function of the data. That provides a best guess to these population quantities. And the second step is to look at the so-called sampling distribution of that statistic under repeated sampling from the population. In this course, we're going to use a different perspective on statistical inference called the Bayesian perspective. And there was recently a mini course on Bayesian, Introduction to Bayesian Statistics that was given last semester. And I encourage you to have a look at those lectures if you have further questions. So we are going to look specifically at the Bayesian perspective, which does make use of the likelihood, but not to find appropriate estimators, but to actually formulate, to actually update prior beliefs about any population parameters. And these prior beliefs are summarized by or are described by a probability model. So here's another definition. A prior distribution models subjective uncertainty about a population quantity using a probability model or probability distribution. Okay. This is also a great way that we can enforce any known hard constraints or soft constraints on our population quantities. Okay, so here's an example. Although the mean vector, mu, is unknown, we may know that it should take values over the entire real line, for example. And is most likely to be around some central value mu naught. And this is subjective likelihood, most likely. And this value mu naught is known. It's something that we would know. For instance, it could be 0, for example. Okay, thus a reasonable prior distribution for mu might be, again, this is a modeling choice that as the applied statistician you're making, but you have to support this modeling choice. So I'm going to model mu as a priori normally distributed with mean mu naught and covariance sigma naught. And these are some assumed central value where mu naught is most likely to lie, and this is how confident we are of that. So for instance, the diagonal entries of the sigma will be, for instance, larger if we are less confident about where mu is. So mu, the prior probability will be more diffuse. We could similarly assign a prior distribution to sigma, but we would need to use a distribution that puts positive probability mass on symmetric positive definite matrices. Okay, and there are such distributions. One example is the Wishart distribution, but we're not going to cover it here. For the moment, let's assume that the matrix sigma is known and that the only unknown population quantity is mu. Okay, so Bayesian inference is based on this quantity called a posterior distribution. So we're going to take this prior distribution that we just defined. We're going to update it by conditioning on the data that we observed. And what we're going to get out is a posterior distribution. And that posterior distribution will capture our subjective uncertainty about the population quantities given the data. Okay, so given any information we have after we've observed the data. All right, so here is the definition. The posterior distribution has the following density. And you can expand this conditional PDF here. As a ratio of the product of the likelihood, the PDF of the joint PDF of the data or the likelihood, and the PDF of the prior distribution. In the denominator, we will have the so-called marginal likelihood. So this is again the likelihood times prior multiplied by the likelihood multiplied by the prior density and marginalized over mu. So we're gonna, it is just the marginal density of the data, if you think about it that way. And we typically don't use this expression that I just wrote down. We typically just use the fact that this posterior is proportional to the likelihood, the density of the observed data, given the parameter, times the prior density. And it turns out that if y follows independent multivariate normal distribution, if y is a random sample from a multivariate normal distribution, then the posterior distribution over mu, if it has a multivariate normal prior, is also multivariate normal. This is what we call conjugacy. All right, so here's an example specifically for the multivariate normal distribution. And then after this example, I will finish the lecture. Let's return to our example with unknown mu. And let's assume that sigma matrix is known. The posterior density of mu is going to be multivariate normal with the following mean and covariance. And as you can see, the mean and covariance have a specific form. So first, I'm going to define this covariance, this posterior covariance, and for ease, I'll define its inverse instead. And it is simply the sum of the prior variance of mu plus n, the sample size, times the inverse covariance of the observations. And mu, posterior mean, is going to be the posterior covariance matrix multiplied by this weighted average of the data and the prior. Right. So this is the prior mean. And this is the sample mean of the data. So there's a nice interpretation here in that the posterior distribution is a weighted average of the prior mean scaled by the inverse prior covariance and the sample mean of the data, which is an estimator of the mean, scaled by the covariance, the inverse covariance of the data generating distribution. Some notes that I'm just going to mention in words here. The strength of evidence is the first thing that we can get from this distribution. As the sample size increases, the posterior precision, that is the inverse of the covariance, posterior covariance matrix, is dominated by the data term. So this term right here. Okay, and in a small sample setting, the prior mean dominates this posterior mean. Something else we can think about is shrinkage. The posterior mean shrinks the sample mean towards the prior mean. In other words, if you have some prior information, you could include that into the prior, and that could help you with your inference. Let's very quickly look at the final R code, which is going to demonstrate what the posterior, prior, and likelihood look like for this example. All right, I have posted some temperature data, which is approximately normal. And we're going to look at this in the univariate case only. We're not going to look at multivariate normal distribution here, just to be able to visualize this a little bit better. All right, maybe I can zoom this out. Oh, I don't know why the legend is so large. I apologize about that. Okay, let's see. So first, let's look at low sample sizes. This is only a single sample, n equals 1. The true value is going to be, I'm sorry, the prior mean is this red line. The data and sample mean, the y bar, the data sample mean is this blue line, vertical line. The red density is your prior density, and the green here is the sample mean of the data. The blue is the posterior density of the data, and the blue vertical line is the posterior mean. So when we only observe a single sample from that temperature data, from a normal univariate normal sample, we can see that the prior distribution is going to overwhelm the data, and so the posterior distribution will be pushed towards the prior. So our inference is going to be a compromise between the prior assumptions and the actual data. That's only when the sample size is small. In reality, we have larger sample sizes. Here are 5 data points, as you can see, from this temperature data. The sample mean here in green is actually now much closer to the posterior mean. So our inference now is weighting the data a lot more than it is weighing the prior. The prior here is purposely misspecified just to show you what's actually happening. And then as you increase the sample size, you can see that the posterior mean gets closer and closer to the sample mean of the data. And furthermore, that the posterior density concentrates more and more. In other words, we become more and more certain about our inference as the sample size grows. So you can play with this code offline and certainly ask Eric or myself if you have any questions. I did get a question on the chat here that I'd like to answer, and it is about the initial covariance. That's a really good question. So the initial covariance, the prior covariance, it is this right here, actually has to be elicited. So it's application dependent. Essentially, when someone says, well, I really don't know anything at all about this mean, or almost anything, it could be any value. So we're going to choose a sigma that is very diffuse. Okay, so we're going to want this normal prior to be extremely, extremely diffuse, quite the density to be quite flat. Okay, we want to be almost for it to be almost equally likely for the mean to be in any region around the prior mean area. If we are actually more certain than that, so if we have some initial idea of what mu should be and we know which range it should be in, you might consider defining sigma naught, choosing sigma naught to be something that makes the distribution a little more highly peaked. Okay, so the choice is up to the practitioner. And so there's a little bit of subjectivity in the analysis, but it does help to introduce soft constraints into your analysis. The prior mean is selected similarly. This would be if you had some prior knowledge about what the actual mean might be. And as I showed you, as the data becomes larger and larger, the sample size becomes larger and larger, the posterior actually starts to ignore the prior more and more, even if the prior is originally misspecified. So we don't have to worry too much about this choice, but we do have to try our best to make these choices as appropriate as possible to describe our prior knowledge about this parameter. I hope that answers your question. All right, so I will end the lecture here. Thank you very much.